Gaussian elimination, uh, named after the very famous German mathematician Carl Friedrich Gauss. Has anyone ever heard of the fundamental theorem of algebra? The fundamental theorem of algebra. The fundamental theorem of algebra says that any polynomial of nth degree can be factored at least one time, uh, where those factors are said to be complex, where complex could mean imaginary and or real part. Um, Gauss proved the fundamental theorem of algebra when he was 21 years old for his dissertation. Um, that theorem had not been proven before. Mathematicians before him had tried for years to prove it, and they could not. One notable mathematician, Leonardo Euler, a very great mathematician, of which we get the bridge between calculus and or algebra and trigonometry. That link in between comes from Euler's formula and other transcendental translations that he gave us. Euler could not prove it, and my professor said if Euler could not prove it, then my professor would say the D thing was just not provable. So, but Gauss proved it. Gauss was a prodigy. He was a genius. His father noted that when the boy was about 6 or 7 years old, his father was in dealing with ossuary science, and he was computing some numbers, and the father was just calling out the numbers out loud and trying to compute them at the same time. He was writing everything down. The boy had already computed the information in his head and told his father what the results were. Gauss was so intrigued by numbers that it fascinated him, but it bothered his father because his father had work to do. And so the father thought one day to just give his son some little math to do on the side, and that'll keep him busy for about 15, 20, 30 minutes. So he said, son, I want you to add up all the numbers from 1 to 100, 1 plus 2 plus 3 plus 4. Just add up all these numbers, summation, 1 to 100. And young Gauss came back in about maybe 2 minutes and told his father the answer. And the father, he's stunned, and it took him a long time to add up the numbers, just to go back and verify. And indeed, his son was right. If you've had calculus 2, you know that the summation of I, as I goes from 1 to n, that's the proof of that is given to us by Carl Friedrich Gauss. That's what he did when he was like 6 years old. Right? So like the summation of I is like n times n plus 1 divided by 2, or something like that. And so he just said 100 times 101 divided by 2, and he got the answer. So anyway, so this is Gaussian elimination. This method, by the way, came to us around somewhere the early 1800s, where there were some astronomers trying to compute the orbit of a star from the Earth, and they could not. They tried and failed. Gauss, who had just in his own spare time just something to play around with, he began taking the data that these astronomers had, and they thought they had missed calculations. He took the data, used an elimination process that bears his name now, and they even thought that what he had was wrong. And then Gauss had calculated the next year, on that particular same date, that star would be in the very same orbit based on his calculations in terms of where it would be, and he was about right. And so we call this Gaussian elimination. We're going to compare Gaussian elimination to the form called Gauss-Jordan form. So what are we doing? We're trying to solve a system. We're trying to solve a system. What are we looking for? We're looking for the solution. If it's a unique solution, no solution, or if it's infinitely many solutions. Now, what's synonymous to this term Gaussian elimination is the term Row-Echelon form. So if you see row echelon form, we're just talking about Gaussian elimination. Row echelon form is in particularly concerned about the matrix. Gaussian elimination is concerned about a system. So for the system, you see x, y's, and z's, right? For the matrix, you don't see any variables. You're still talking about the same thing. So you have Gaussian elimination, which is row echelon form. The form that's even stronger and better, the one that I prefer, is called the Gauss-Jordan form, or reduced row echelon form, where you're going to try to go all the way. So steps 1 through 4 define row reduced echelon form or Gauss-Jordan. Numbers 1, 2, and 3 define Gaussian elimination or just row echelon form. But what do they say? Well, let's go over it. Most important. Now remember, we only have 3 elementary operations. To try to manipulate a matrix or a system, we only have 3 things we can do. We can interchange the rows, we can add the multiple of one row to another row, or we can multiply a row by a non-zero constant. So here, all rows consisting entirely of zeros are grouped at the bottom of the matrix. Right? So if you have a row, if you have 3 rows, if the second row is all zeros, put it at the bottom. The first term in any row is a 1, called a leading one. Well, what if it's not a 1? Well, the previous examples showed us that you can get it to be a 1 by using the elementary row operations, right? Like if it's 2, 4, 6, 8, who do we appreciate? Just divide by 2, right? So and so then you have, for that first term, you have a 1 there. Or, you know, if it's the first term is a 2, and then the second row, that first term is a 3, then you can say negative times row 2 plus row 1 to get a 1, or a negative 1 there in that first position. So the first term in any row, when you look at the first term, you hope, you want it to be a leading 1. If it's not, then you have to do some math manipulation to get it to be that. Yes, sir.
It doesn't matter if it's a negative 1.
If it's a negative 1, you just multiply by a negative and you get a positive 1, right? For 2 successful rows, look at, let's say, for example, row 2 and row 3, or row 2 and row 1 and row 2, or look at rows 2 and row 3, or rows 3 and row 4. Successful, right together, stacked on top of each other. Look at 2 rows. The leading one in the upper row occurs further to the left than the leading one of the next row that falls below that. So the idea of it is that eventually you want to have on the main diagonal, if possible, the leading ones, and then zeros under the main diagonal. And so we get the idea that we're going to walk up the stairs. I used to be able to do that, you know, on the main diagonal. Well, that was in a dream. I thought I was doing that, but yeah. Moonwalking. For each row that has a leading 1, then that row has zeros elsewhere. So if you just stop at 1, 2, and 3, then we have row echelon form, or Gaussian elimination. If it's 1, 2, and 3, then you have to back substitute to be able to solve for the rest of the variables. But if you incorporate step 4, then you've solved the system automatically within the whole matrix. That's why I like to do 1, 2, 3, and 4. In other words, for the matrix, I want to try to build a leading 1 on the main diagonal, and then wherever that leading 1 is, in its column, I want to get zeros elsewhere. Now, what I've just said, I've explained down here below. So statements 1 to 3 defines Gaussian elimination, or row echelon form. Statements 1 through 4 define Gauss-Jordan form, or you can call it reduced row echelon form. The word echelon is a French term that just means stair pattern or ladder, and so we get the idea of steps. If it's Gaussian elimination, then you have to use back substitution to finish solving the system. Now here's a matrix or a system that is in row echelon form. So it's not reduced row echelon form, it's just in row echelon form. Well, you say, well, there's no leading 1. Well, there's not, but we get the idea that here I have this term here And then up under that term, I have zeros there up under. Then I move to the next term. Then if this was a leading 1, I have a 0 up under it. Now you can make this a 1 by just dividing by 3. You can make that a 1 by dividing by 4. I just want to show you that this is indeed row echelon form. It's like a stair step. What does that mean? Well, here I can solve for z, right, quickly. And then from that value of z, I can solve for y. So I'm going to just walk up the steps, right, to get y. Then I take the values of y and z, plug them here, I can solve for x. That's back substitution, right? So that's Gaussian elimination. Now, if it was Gauss-Jordan or reduced row echelon form, this negative y would be gone, that 3z, would be gone. This plus z right here would be gone. All you have would be just terms on the main diagonal. And then whatever you have for this number, hopefully you can divide it out and get a 1 there, and then that'll be the answer for x. This will be the answer for y, and then the answer for z. So here, notice that z is equal to -2. Why does it do that? And then we have 4y here plus z, but z is -2 is equal to 10. So we get 4y is equal to 12. Y is equal to 3. And then we back substitute for y and z to solve for x. So we get 3x minus y, that's minus 3, plus 3 times -2 is equal to 12. So we get 3x minus 9 is equal to 12. 3x is equal to x is equal to 7. Now, my question, is this the unique solution, the no solution, or infinitely many solutions? It's unique, right? If it's no solution, it's going to be some mess. And if it's infinitely many solutions, you're going to basically get like either a whole row of zeros, or you have 2 equations and you got like 3 unknowns, right? So good. So this is the unique solution. X is 7, y is 3, and then z is -2. But to get a system in row echelon form takes work. To reduce to echelon form, we must utilize the rules for Gaussian elimination. The elimination method applied to systems with more than 2 equations. Now again, the 3 elementary row operations, that's what we use to be able to get the system in row echelon form or reduced row echelon form. I want to give you the steps now for Gaussian elimination, then I'll give you the steps for Gauss-Jordan form. I have them listed for you. So let's take this system here, and so it's A11 times x plus A12 times y plus A13 times z is equal to b sub 1. Now the subscripts for A just hold the position of that coefficient. So A11, the first number, denotes the row position. The second number denotes the column position. Right? So this is row 1, row 2, row 3. And this is column 1, column 2, column 3. So A11 is the first row, first column. A12 is the first row, second column. A13 the first row, third column. Right? So for Gaussian elimination, what we're going to do here is to use this A11x to cancel out what's beneath it, the A21 and the A31. And then once you've done that, we're going to use the second step is to use A22 to get rid of the A32. Once you do that, it's going to look like this guy right here. Okay? And then, from there, if it's Gaussian elimination, you have to use back substitution for y and z to solve for the value for x. Sometimes it does not matter on the order of reduction as long as you have one equation with 3 terms, one equation with 2 terms, one equation with 1 term. And here I'm thinking ideally about a system with 3 variables and 3 equations. All right. So, examples, if the system has a unique solution, then the solution will consist of some value for a, or x of 1, some value for x of 2, some value for x of 3. And we say the solution point is parentheses a, comma b, comma c. Now, I'm going to work one of these problems, but I prefer to just give you what I always use. And what I always use is Gauss-Jordan form, that is reduced Row-Echelon form. I mean, that's the whole goal anyway, so I just solve everything like that. And so when I'm finished with the matrix, I'm done. I get my answer, and I move on. With Gaussian elimination, you reduce that matrix, but it's like halfway done. You have to go back and back substitute with the algebra. Well, who cares about that? So let me state here the Gauss-Jordan form, the ideal form, and then we'll come back and work a problem or two, and then we'll go home. So here, the Gauss-Jordan form. To put a system in reduced Row-Echelon form, consider a 3x3 system, a system with 3 equations, 3 variables, x, y, and z, or x of 1, x of 2, x of 3. And you can write it as a matrix over here. So again, the row position, the column position. So this is what I prefer. So here, to get the matrix reduced into the so-called reduced Row-Echelon form, we get a 1 at A11. That's our leading one. And the next thing we're going to do is to use A11, or that 1, to get zeros at A21 and A31. Right? Now I'm going to deal with the column first. So it's column 1, reduce that, 1 and zeros. Then I move to column number 2. Column number 2, the first thing that I want to get to is the most important entry, and that is A22. I want to get a 1 there. Right? This is step number 3, get a 1 at A22. And please, I beg of you, friends, to, if you go on the blackboard, this is already there. Just print it out and, just come to class. So I don't want to have you to try to write everything down when everything is right there. And so, what I want you to write down is whatever I do extra in terms of solving the problem, so you won't get lost in terms of what we're doing. So here, that's step 3. Get a 1 at A22. Once you get that, then you get zeros above it and below it. Right? That's the next step, step number 4. And then you move to the third column. You get a 1 at A33. Use that 1 to get zeros above it. Right? Now there's some wiggle room with that, but the idea is once you've dealt with a column, you move to the next column. You want to have zeros on the left side, because if not, do you know what a transgression is? It's when you clean something up and you go back and mess it up. If you don't have zeros behind you and you try to go and get zeros and 1s in front and you got numbers behind you, you're going to keep on adding to that. And so instead of reducing, because 0 plus 0 is always 0, so I want to have a 0 behind me. If not, then you think you're fixing something over here, and just like my kids, you're going back and messing something else up over here, right? I told my little one, I just got through mopping the floor, so don't walk in the kitchen with your muddy shoes on, because they've been outside playing, And he comes in the house with this bucket of fish that he's caught down there at the pond, and he took his shoes off, but he's carrying a bucket and he's spilling stuff from the bucket all over the floor. So he said, "Daddy, I didn't wear my shoes," so he didn't put the mud on the floor. But thank you, you got fish gunk all on the floor now from the bucket. Transgression. So anyway, and you'll see what I mean if you ever run into this with these matrices. Okay? So that's Gauss-Jordan form. That's the form that I like. So now let's go back up here, and I'm going to work a problem. You take this guy right here. I'm going to put it in the matrix format. This is 1, 2, 3, 1, negative 1, 0, 1, 1, negative 1, 6, 3, 0. Right? So get a 1 at A11. There's already a 1 there. So I move on. I use A11 to get zeros beneath it at A21 and A31. So to do that, we'll say negative 2 times row 1 plus row 2. And then after that, we'll say negative 3 times row 1 plus row 3. So row 1 stays the same. So here, this is negative 2 times 1 is negative 2 plus 2 is 0. This is negative 2 minus 1 is negative 3. This is negative 2 plus 1. Negative 2, negative 1. And then this is negative 12 plus 3, negative 9. And then now negative 3 times row 1 plus row 3. So this is negative 3 plus 3 is 0. This is negative 3 times 1 is negative 3 plus 0 is negative 3. This is negative 3 minus 1 is negative 4. And then this is negative 18 plus 0 is negative 18. Right? So now I've dealt with the first column. I move to the next column. I want to get a 1 at A22. Right? But I noticed that there's similarities between this number and the number right up under it, right? So, I mean, if that's the case, then you kind of want to use that to your advantage and cancel out something if you can. So what I'm going to do is to take this row number 2, just multiply it by a negative. Just say negative times row 2. So now let's use this 3 to our advantage and get a 0 there. So we'll just say row 2 plus row 3. We'll make sure that we get the leading 1 there, but we can use the numbers to our advantage, manipulate them. You control the number doesn't control you. Right, so we're just adding row 2 plus row 3. So this is negative 3, this is negative 9. Okay. Good. Now, well, here they said we want to use Gaussian elimination. So for Gaussian elimination, you want to get a 1 here, or you can solve it, directly by just based on what it is. But I'm going to do this. Let's say here negative 1/3 times row 3. Zero, 0, 1, and 3. Now, do you see that where this 3 is here at A22, if I divide through by a 3, I'm going to have 1/3 right there, which, I mean, it's okay. If you want to deal with the fractions, that's fine. Is it a way to overcome that? I believe it is. Now let me ask you, you see where this 1 is here? Can I use that 1 to get a 0 where that 3 is? say for example, if you say negative 3 times row 1 plus row 2, will that give us a 0 there? Well, it would, but it'll give us something else here besides 0, right? So that's what I mean by the transgression. You want to watch out for that, right? Here's what I see. It may be possible to take this 1 and go ahead and get the 0 there, take that 1, get the 0 there, and then divide through by that 3 and get the 1. To hopefully save us from having to deal with fractions. So what I'm going to say here is negative times row 3 plus row 2, negative times row 3 plus row 1. Let's do row 1 first. Right? Because there's 1's above it, so So just negative times row 3 plus row 1. I do that, that's going to give me a 0 there. So this is 1, 0, and then this is negative 3 plus 6 is 3. And then negative times row 3 plus row 2. So this is 0. So 0 with this guy plus 3 is still a 3. This is negative 1 plus 1 is 0. And then this is negative 3 plus 9. We get 6. Now let's see. Let's get a 1 here. I can do that now without having fractions by simply saying 1/3 times row 2. This is 1, 1, 0, 0. Oh, so 3. This is 0, 1, 0, 2, 0, 0, 1, 3. Right? So now, one more thing, to have this in reduced Row-Echelon form, use this 1 to get a 0 above it. So that's simply negative times row 2 plus row 1. So we get 1, 0, 0, and just leave that there. This is 0, 1, 0, 2, 0, 0, 1, 3. So negative 2 plus 3 is just 1. Now if this is reduced Row-Echelon, right? If it's reduced Row-Echelon form, then the answer is contained within the matrix itself. Here, this says that x of 1 is equal to 1, x of 2 is equal to 2, and x of 3 is equal to 3. Huh? Well, let's see if I can run through number 2, and then I'll be done. How does a problem look when it has no solution? Well, here I tell you, but then let's look at the example to see if it matches. If the system has no solution, then you will reduce a row to 0 equal to some number where that number is not 0. Right? So that's what I call mess. Right? You get 0 equal to 5. Well, that can't be, right? There's no solution. So let's put this in the matrix form. 1, 1, 2, 0, 1, negative 1, 4, 10, 2, this is 1, 10, negative 5. Right? So we have a leading 1 at A11. We use that term to get a 0 here at A21, and then use this 1 to get a 0 at A31. So this is negative times row 1 plus row 2. Then negative 2 times row 1 plus row 3. So row 1 stays the same. So just negate row 1, add that to row 2. And then negative 2 times row 1 plus row 3. So this is negative 8 plus 2, negative 6. And this gives us negative 2 minus 7. Well, negative 2 minus 5 is negative 7. So now, what we're going to do, we're going to use this 1 at A22 to get a 0. You already have a 0 above it. Just use this 1 to get a 0 below it. Let's see what happens. So you just add row 2 plus row 3. Zero, 0, 0, 2. Right? Now let's interpret this system. This is x in terms of x, y, and z. So this is x plus 4z is equal to 1. That's the first row. The second row says this is y plus 6z is equal to 9. The third row says 0 is equal to 2. See that? Can't have that, right? No solution. Right? So now you should be good to go to do the homework for section 1.2. So 1.1 and 1.2. If you have any questions, please feel free to ask. And what I will do is on Monday at the beginning of class, I will ask if there are any questions. There could be questions from one or two things. It could be from the homework online, or it could be from the homework in the textbook.